Alright, welcome to Chapter 3, Section 6, Forced Oscillations and Resonance. So basically this chapter is examples on how to solve homogeneous differential equations or applications. So that's basically the way I'm going to treat it, and so let's get started. So you've got this differential equations that we've seen before, at least part of it we've seen before, right? The second derivative, m times the second derivative of x plus c times the first derivative of x plus k times x has been equal to 0. We've done that before with oscillation methods, but this time we're going to give it a driving function of f of t, and what's going to happen is what they talk about, your natural frequency is going to be omega naught, which is equal to the square root of k over m. And then the driving function can either be some constant f0 times the cosine of omega, which is the driving frequency, which is different than omega naught. Omega naught is the natural frequency of this. And then, or it could be, let's do an example. So this is problem 1 on page 206, and we've got this undamped oscillator, and it's driven by this function. So from that, I can determine that omega should be 2, f0 should be 10, and the natural frequency should be 3. And then you find the roots for this equation, you find that they're imaginary, and so you would get that for the characteristic equation. And then you need to make a prediction for the particular solution. So that's my prediction based on f of t. And so I have to find its first derivative, I have to find its second derivative, and then I have to add to its second derivative 9 times its function. And so if I do that, I get this. Now this has to be equal to 10 cosine 2t. And so you get these two equations that come from that by trying to make the coefficients equal in front of the cosine term and the sine term. Since there's no sine term, the coefficient on the right hand side of the equation for the sine is 0, and that gives us 5b equals 0 or b equals 0, and then you can solve for a equals 10. So our particular solution will be this, and so if we plug them back in, we get that type of solution, but we need the constants c1 and c2. So they give us this initial condition that the position and the first derivative of the position is equal to 0 at t equals 0. So we're going to plug that in. So the position of the function at t equals 0 is 0. So that's going to allow us to find that c1 equals minus 2. And then the first derivative of the function is 0 at t equals 0. So that's going to basically tell us that c2 equals 0. And then, so that's going to be our solution. So you have two terms here. One that is the controlled by the spring itself, and one that's controlled by the damping function. So if we make a graph, okay, so what do we get from this? Well, I know omega naught is 3, and if you want to write this in terms of the c times cosine of omega naught t minus phi, we find out that phi is going to be 0, c is going to be minus 2, and our driving function is going to be 2. But what is our amplitude of that driving function? Well, if you solve this, the book likes to write it in this format, where F is the driving force. In our case, that's 10. Our mass is 1. Our natural frequency is 3, but 3 squared is 9, and our driving frequency is 2, but squared is 4. And if you solve for that, that comes out to be 2. So now if we graph our functions, so we're going to graph three things. We're going to graph the total solution. We're going to graph the solution associated with the spring itself, and the solution, the particular solution, basically the characteristic solution and the particular solution. So if we do that, we find out that the red graph is our solution to our non-homogeneous differential equation up here. Now the black one is the solution, is our particular solution, and the blue one is our characteristic solution for our initial conditions. And you can see as it goes along, we get large amplitudes of 4 every so often, and very small amplitudes of 0 every now and then right here. And so we can go out as far as a +4 in the x direction and a little over -3 in the minus x direction over time. But you can see how it's periodic. It repeats this every maybe 6 or 7 time units, I think, because this is about, that's 5, so that's 6, so that'd be 4, and this is about 9. So yeah, everybody about 5 time units. It completes a total period of oscillation. But you can definitely see how the oscillation changes over time. And this is a an example of forced oscillation, and you can see at particular times the amplitude gets large, and at particular times the amplitude gets small. Resonance is a particular time where the amplitude reaches maximum based on the frequency. Alright, so here's another differential equation. This one is damped. We have a C divided by M of 3. So let's solve this one. So from this, you got to join these into one function using the method I've showed you in class. We're going to use the property of the cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. And if you do that, you can figure out that the F0 is going to end up being 10, and your driving frequency is going to be about 3. So I shouldn't say the driving frequency should be 3. The driving frequency is going to be 10. The natural frequency should be 3. So if you solve the non-homogeneous differential equation, you get an imaginary root. You get 2 of them. So that's going to give us this solution for the particular equation. And you notice there's an exponential in here. And so as t gets large, this exponential is going to get small. So this part's going to go away. When that happens, as t goes on, this contribution to solution is going to be small. So that basically is called the transient part of the solution. And then we have to find our particular solution, and that's our initial guess. And of course we take our derivative and our second derivative, and then we're going to add to our second derivative 3 times our first derivative. We're going to add also again 3 times our function. And if we do that and add them up, we get this. That has to be equal to the right hand side, which is of this order. So we have to group the coefficients. So if we group the coefficients, we get this equation and this equation. And if we solve that system of equations, we get this A and this B. So this is our particular solution. So we're going to add them together. Excuse me. We're going to add these together. And then again, you get this part of the solution has this exponential term. As t gets large, e to the minus t is going to get small. So over time, this will disappear, and all we're left is with this solution. So they like to break these into 2 types of solution. This is what they call the steady periodic solution right here. The one without the exponential is the steady periodic solution. And the one with the exponential is called the transient solution, because over a period of time it will disappear. It goes away, so they call it the transient solution. And that's how you solve some of these forced oscillation problems. And you can graph this and then get this very interesting solution that shows up. And I'll leave the graphing up to you. You are going to have to do investigation 1 on page 208. And again, it deals with this differential equation that we've seen before. Now, here's how I'm going to recommend you solve investigation 1. I need you to read the information about the investigations on page 208. If you do that, you should be able to figure out how you can pick a value of P and Q. You should be, after you do that, you should be able to determine the values of M, C, and K for our differential equation. Once you've done that, you can look at investigation 2 on that page, which gives you the maple commands you need to use to solve investigation 1. So let me state that again. Investigation Q just gives you commands to use in maple. So it shows you how to set up the differential equation. It shows you how to use the desolve command with initial conditions. And it shows you how to use the simplify command and the combine command. And it uses a command, the ampersand command. And then it shows you how you're going to graph your functions over time. So, what I would suggest is you use those commands, but that to help you solve investigation 1. The initial conditions for the differential equations are given in equation 3 on page 208. What you have to do is choose your function f of t, and that is given in investigation 1. So good luck, and I'll see you in class.